Hi guys, welcome back to Think Tank Online Learning. This video I want to talk about Stokes Theorem. Okay, so we're given a question. Let S be part of the cylinder C equals to y minus x squared for we're given the limits of x, the limits of y, and want to verify Stokes Theorem. Okay, if a vector function xy I plus yz j plus xz k. So I'm going to draw this surface here, but I'm going to draw this surface the moment I will perform a line integral. Okay, so this is the Stokes theorem. Okay, so this is equal to the line integral for a closed surface f to r. Okay, so what I'm going to do, want to perform the line integral using Stokes theorem. Okay, and perform the line integral without using Stokes theorem. Okay, so this is going to be a long way, but we have to do that since we want to verify Stokes theorem. Okay, so the formula for Stokes theorem, we're going to find the curl. Okay, the curl of this function f. Okay, so this is going to be the curl of f. Okay, and after that we're going to find the normal and find the s and perform our double integral. Fortunately, our limits are very easy to dictate. Okay, so what I'm going to do here, I'm going to compute the curl of this vector. Okay, so the curl, I'm going to find the curl. So first I'm going to find here for the I component. Okay, so I'm going to say I. Okay, so this is the row for I, this is the column for I. So I'm going to say partial y times xz, okay, minus partial z yz. And what if I do that? Look, we don't have any y component here, so if we differentiate with respect to y, this is just a constant, it's going to be 0. But here, if we differentiate with respect to z, we're going to get negative yi. Okay, good. Then we're going to j, but we have to put a negative. Okay, so j, this is the row for j column, so I'm going to say partial x of xz minus partial z of xy. Okay, we have x component there, so we're going to get negative z. Okay, if you say we have z, if you define with respect to x, we're going to get z, but if you define with respect to y, we're going to get 0. Okay, so it's going to negative j times x, so we're negative z j. Then for the k component, row for k, column for k, so we're going to partial x for yz minus partial y xy. And if we do that, here we don't have any x component, so we're going to get 0. But here, if we define with respect to y, we're going to get x, so x times k, so it's going to be negative xk. Okay, so if you notice an error in my video, okay, just feel free to let people know in the comment section. You know, it's mathematics, sometimes we'll be rushing, we may make some mistake. Okay, so now we have our curl. So the curl is equal to negative yi, negative zj, negative xk. Okay, what about finding the normal? Okay, so the normal, this is the equation of our surface, so I'm going to use the same equation to find the normal. So I'm going to say, okay, so here let me first write this function z is equal to 1 minus x squared. Okay, so I want to create a new function, so that function is going to be g. So that means g is equal to, but I want to include z, x, and y. Okay, so g is going to be, if I arrange this, it's going to be z minus 1 plus x squared. And we don't have any y component, but we're in space, so the y component is 0. Okay, So now I want to find the normal. Okay, so the formula for normal n is going to be the function we named, in this case I said g, the gradient of that function g over the magnitude of g. Okay, so this is going to be the normal. Okay, so let's find the gradient of g. So we're going to take the partial derivatives of g with respect to y, to x, y, and z. And if we do that, we take the partial derivative of g with respect to x. What we're going to get, 2x I. Then for the y component, we don't have y component, we're going to get 0. And for z component, we just have z. So we're going to have k, which is equal to 1. Okay. Then what about the magnitude of this? So we just say x squared, y squared, plus z squared. And for x squared, we're going to say 2x to the power 2. For y squared, we don't have 1 squared, is 0. But for k, we have 1 to the power 2. Okay, and we're going to check the square root since it's the magnitude. Okay. And forget say over here. Okay. We're not going to simplify here. I'm going to show you why we're not going to simplify. Okay. And now we're left with the ds. So ds is equal to, this is ds, is equal to the square root of g, partial, the derivative of g with respect to x, partial derivative, then partial derivative of g with respect to y squared plus 1. Okay, so this is 2. And after that, I'm going to put a square root. Okay, so that means ds is equal to, okay, let me write it here. So ds is going to be equal to, okay, the partial derivative of g with respect to x is just 2x, and the partial derivative of g with respect to y is 0 plus 1. So it's going to be 2x squared, since we have a squared here, plus 0 squared plus 1. Okay, so if we look at our integral, this is the dot product. Okay, so what I'm going to do, I want to find the dot product of f, of the curl of f, and the normal. Okay, so I'm going to say here the curl, this is the curl, so it's normal. Okay, so the curl, I'm going to write it in coordinate form. Okay, in column form, we have negative y, negative z, negative x times the, with the normal here. So the normal, this is same as saying, okay, unfortunately I can't write it in the column form since I run out of space. 2x I plus k. Okay, I'm not going to include the denominator, because if we say n times ds, we should see that ds is equal to the, is the same as the numerator of the normal, so this is going to cancel out. Okay, so if we say I component times the I component, we're going to say negative y times 2, so it's going to be negative 2xy. We no longer have the units. And for z, for y component, here we have negative zf with 0, and for here, for the k component, just have x and 1, so it's going to be negative x. Okay, so now I'm going to set my double integral. So this is going to be the double integral. So we have the cross product. Okay, so the cross product is negative 2xy minus x dy dx. Okay, some of you may wonder where did ds and what happened here. Okay, so I'm going to show you. Let me just find a piece of paper so that I don't run out of space here. So we say this is the formula. So the double integral of curl. Okay, so this is the curl, this is the equation of the curve, just right here. So it's going to be negative y I negative z j negative x k. Okay, the dot product of the normal, this is the normal. Okay, so the normal is negative is 2x I plus 0 j plus 1 k over the square root of 2x squared plus 1. Okay, then we have ds. What is ds? So this is ds, the square root of 2x squared plus 1 dy dx. So as you can see, this and this will cancel. So what we're going to do, I'm just going to find the dot product of this one and this one, and that is what I've just done here. Okay, so we're good. What are my y limits? Okay, since x is my outer, so I'm going to integrate with respect to y first. So these are the limits for x from 0 to 1, and for y from negative 2 to 2, negative 2xy, negative 2xy minus x dy dx. So let's integrate with respect to y first. So we're going to get 1 0. Okay, so if we integrate negative 2xy, we're going to treat x as a constant. So it's just same as saying negative 2xy to the power 2 over the new power 2 minus x y, and our limits, what are our limits? 2 and negative 2 dx. Okay, I'm having a problem with my mathematics. I don't want to change the color to red. Okay, dx. Okay, so now what we're going to do is that, okay, you should know this is this and this will cancel. Okay, so I'm just going to say the upper bound minus the lower bound. Okay, so the upper bound is 2, the lower bound is negative 2. Okay, so if we do that, we're going to get the integral of 1 to 0 negative 4x dx, and if we integrate with respect to x, we're going to get negative 4x to the power 2 divided by the new power. Okay, and our limits 1 to 0. Okay, so if we do this, we're going to get negative 2. Okay, now I want to perform line integral so that you can verify. So what we're going to do, we now want to perform the line integral. Okay, so this is the surface c equals to 1 minus x squared. Okay, I think when we are now computing the line integral, I think it's very, very wise to draw the surface which you are looking at. Okay, so what I'm going to do here is I'm going to choose a starting point. Okay, so I've shown you that the line integral for a closed surface, you can just add line integral from here to here to here to here. Okay, so I'm going to start at A. Okay, so this is my graph. Okay, so my graph, the length of this cylinder, okay, the length of this cylinder is from 2 to negative 2. By the way, this is the origin. Okay, so I'm going to start from A and go to B, right? Remember, there's nothing here, but it's not closed here. From A then to B. Okay, then after going to B, I'm going to from B to C. Okay, so this is the line. This is not the line, just A. Okay, then from C we're coming to D. Okay, then now from D I have to go back to A so that the path should be closed. Okay, and this vector is not conservative. Okay, so what we're going to do is that we're going to perform this line integral. So first I'm going to start with a b. Okay, r, this is our vector function, and I is dx, j is dy, and k is dz. Okay, then from A to B. Okay, so I think it's very wise if I list the coordinates here. Okay, for A For a, this is the y-axis, so x equals to 1 for a. X here, x is 1. Okay, then what about y? Y for a, y is 2. Okay, for b, or back here, x is 0. Okay, x is 0. Then y is 2. Then for c, x is still 0. Y is now -2. And for d, x is now 1. Y is -2. And you should remember z was 0 here, and here. Okay, we're not going to perform this line integral. This is not a line. I just shown you that it's just a, you have a closed curved surface here. Okay, okay. So for AB, if you look at AB, what is changing? Okay, so since this is in space, I should have written 0, 0, 0, 0. Those were in 3 dimensions. Okay, so from A to B, we have a curve. Okay, and what is the equation of the curve? The equation of the curve is, so let me just say FAB FDR. Okay, so the equation of this curve is 1 minus x squared. Okay, so it's z equals to 1 minus x squared. So that means I'm going to say x is equal to x. Okay, but what about z? Z is equals to y. Y here, y is 2. Okay, y is 2 from here to here. As you can see, y is not changing. Y is equal to 2. And for z is equal to 1 minus x squared. Okay, and that means I don't need dy and dz. I want to put it in terms of dx. So here, if I say dy dx is 0, then here dz dx, if I perform dz dx, I'm going to get -2x. So this means dz is equal to -2x dx. Okay, so yeah, just set x as my parameter. Okay, and what next? We're going to say the line integral AB f dr is going to be the integral of x. This is the initial point. Okay, x is 1. It's initial. Then the final x is 0. I know if you point this in some calculators, may say that the upper bound should not be lesser than the lower bound, but in line integrals it is possible, and it's possible. Okay, then we're going to say x, y is 2, it's a number, and we have dx plus y is 2, z 1 minus x squared. Unfortunately, dy is equal to 0, so I'm going to get 0, so I'm going to save space. Then for x, we have x, z, it's 1 minus x squared. Then for dz is same as saying -2x dx. Okay, so let's perform this integral. Okay, so we're going to get 0, 1. Here it's 2x, factoring out dx. So here we're going to get x times 2x, -2x squared times 1. So it's going to be -2x squared. -2x squared times -x squared. So that is going to be +2x to the power 4 dx. Okay, and if we perform this integral, we're going to get the integral of 2x squared over 2 minus 2x to the power 3 over 3 plus 2x to the power 5 over 5. Our limits 0 and 1, and the answer here is equal to 11 over 15. And now want to go from B to C. So this is a straight line, okay, from B to C. Okay, I'm going to take a new page. Okay, so the line integral from BC, okay, then integral from BC F to R. Okay, so we're still using, we said x equals to, so in this case our coordinates from B to C. Okay, so if we look here, x is not changing, okay, but y is changing. So we're going to set y is our parameter. Okay, so if we set y as our parameter, y is equal to y, then x is 0 here, x equals 0 here, then x is equals to 0, then z is 0 also. Okay, at this point z is 0 also, so z is equal to 0. Okay, so that means line integral of our vector function, okay, of our vector function is equal to xy, so that is going to be equal to 0. Okay, then y times z are going to get 0. Okay, then the limits, y is from 2, lower limit, the upper limit here, -2. Then xz, that is equal to 0 also, dy. Okay, and if we integrate here with respect to y, what we are going to get is equal to 0. Okay, and now want to move from C, okay, from C to D. Okay, so from C to D, this is the curve, and to say the equation of this curve is equal to z is equal to 1 minus x squared. Okay, and like we did when we find the line integral of AB, we said x is equal to x. So as you can see here, what is not changing from CD, y is not changing. Okay, what is changing is x. So x is going to be our parameter. So we said x is equal to x, y is equal to 2, and z equals to, in this case, z equals to 0. Okay, so sorry, z equals to minus x squared. Okay, so what we're going to do, we're going to find the line integral for CD F dr. What is changing? X, initial 0, final x is now -1. Okay, so it's now 1, positive 1. Okay, and we have x, y, we have x. What is y? Y is -2. Okay, so that is going to be y dx plus yz, z is 0 here, z is equal to 0. Okay, plus yz, so we're going to get 0, plus xz, we're going to say x, what is z? 1 minus x squared. What about dx? dz said it's equal to -2x dx. Okay, so this is going to be our integral. Okay, so if we integrate here, you're going to say, let's simplify it first, -2x, okay, minus 2x squared plus 2x to the power 4 dx, and to get, okay, so it's -2x to the power 2 over 2 minus 2x to the power 3 over 3 plus 2x to the power 5 over 5. Our limits 1 and 0. Okay, I just realized that when you perform line for AB, if we say upper bound minus lower bound, we're going to get negative here. Okay, I forgot to write negative. I'm sorry for that. Okay, so if we punch this in your calculator, we're going to get, so this is equal to be negative 19 over 15. We have performed the integral of d a f t r. Okay, since we write d to a, and this is a line. Okay, so we know that z is 0 here. Okay, so want to say what is changing? Y is changing from negative 2 to 2. So I'm going to say y is equal to y. Okay, what about x? X is just equal to 1. Then z is equal to 0. Okay, so our line, our vector function, which is f is equal to x y dx plus yz dy plus xz dz. Okay, so if we say dy dx here, as you can see, we don't have any y component, so we're going to get 0. So the line integral here is going to be the integral. Y is changing, the lower bound negative 2, the upper bound 2. Okay, so we're going to have x times y. Okay, x is 1 and y, but dy, we don't have any formula for dx, because if say dy dx here, going to get 0. So this is going to be 0 plus, and here yz, we know z equals to 0, we're going to have 0 plus xz, z equals to 0, so automatically we're going to have 0 plus dy, and this is equal to 0. Okay, so now we said our formula. Okay, we're going to find the addition of our line integrals. Okay, so we're going to say f, it's now a closed surface, c dr is going to be our answer. Okay, so our answer, we had 11 over 15 plus negative 19 over 15 plus 0 plus 0, and this is equal to negative 2. Okay, so negative 11 over 15 here, then we have 0 here, negative 19 over 15 here, 0 here. So this is equal to negative 2, and when we compute Stokes theorem, also get negative 2. So that means we verified the Stokes theorem. Okay, so this is the Stokes theorem, and yes, is equal to the line integral of a closed surface, since negative 2 is equal to negative 2. Thank you for watching. I hope for your comments and likes.